So these are in the unit of logarithm. So this is 1,000, 10,000, and more. So after thousands of cycles, the strength of the material, basically you can think of either the yield strength or ultimate tensile strength, basically the strength. Sorry. The strength reduces, drops. So after certain cycles, the strength drops. So over here, this unit is in KSI. From here, this is steel. How come there's no measurement before this? Because metal are quite strong, and this amount of cycles doesn't change anything. So it starts with some measurement after 10,000 cycles. And you can see that after certain measurement, the strength of the material drops. But it sometimes, for some material, it will stay at certain like a saturation point. And for some other material, it could be dropping more, but maybe the slope changes a little bit. Okay, so it really depends on what kind of material you are using. Different material has different material behavior. So how can we put this into our design? We call this dropping strength endurance limit. Okay, or sometimes people call the fatigue strength. So it's gonna be the value of the stress at which value occurs after NF cycles. Okay, so in order to measure the endurance limit, there are usually certain experiments, standard experiments. Okay, so what the usual case is they will apply certain amount of force. So one example is, let's say they apply some stress, apply some force to introduce certain stress in the material. And if the stress level is like a stress 1, okay? And this is gonna be fluctuating. So with fluctuation, and usually they will apply this as a like a reverse cycle. Okay, so it will be something like this, like a sine wave. Okay, so this amount is sigma 1. Okay. So they will apply this, and then for a certain amount of cycles, for n cycles, then they realize, okay, failure. Right? So they know when they apply this amount of stress with this amount of cycles, it will fail. And of course, this experiment has to be done for multiple times. And you will, of course, get some uncertain data, meaning every time you perform this experiment, the result may be different. So they definitely has done this a lot of times, and then you take some average. So it's like if they apply this amount of stress, and they realize up to this amount of cycle, the material fell. Then they define this is the endurance limit for that amount of cycle. Okay, and if you change the amount of stress, let's say a greater amount of stress, and they have done experiments and realized the material cannot last same amount of cycles. The number of cycles drops. So greater stress means the amount of cycles will be smaller. Okay, and usually when we are designing for fatigue problems, we because for many metal materials there is a this saturation point. Okay, and afterward the endurance limit doesn't change too much. So usually this is happening at 10 to the power of 6 cycles. Okay, and in our design, we will use the endurance limit for 10 to the power of 6 cycles as the design parameter. So it's kind of like a prediction. We predict after 10 to the power of 6 cycles, the material strength actually drops to certain stress level. We are going to use it in our design equation so that our design can actually last at least maybe 10 to the power of 6 cycles. Okay, so um, later on when we do some analysis, we will apply a number, the endurance limit, into the equation. Basically, it's gonna be this number. The stress level representing the strength limit for 10 to the power of 6 cycles. Okay? Um, I have read different versions of the textbook, and they all have different ways to use the symbol in this particular chapter. So over here in the textbook I'm using, I think it's Shigley. Uh, they are using N and A representing mean value and amplitude. So E represent mean, A represent amplitude. Okay. So how do you get for this particular fluctuating stress? Is not the amplitude is not the same. So how do you in the future problem solving? What do you do? Usually they handle the worst case. They just use the largest one as the amplitude. Because in mechanical design, we want to consider the worst case. And of course, if this only happens once in 10,000 cycles, then you are too conservative. This only happened once. I mean, in mechanical design, being conservative is not a bad thing, right? Because maybe we are designing for something important that could hurt someone if the component fails. So sometimes it's okay to be conservative. If you study the like frequency of the amplitude, and you realize, hey, this amplitude happens more. So let's just use this one as my consideration for the amplitude of fluctuation. Then you are a little aggressive because you want to take a risk. And later on, when this is happening, this may make your make your component fail. That's why most of the time we are usually conservative. Okay, so in some of the books there are symbols using this way. They use AVG and R right here. So this is average, and this is range. They call this They call this range stress. But it's the same thing. It's like the amplitude, the amount of fluctuation. Okay, so they're just names. So later on, if you read some other book, uh, the most confusing part is there's an A right here, and there's average. So also starts with A. So in some books, you may be confused by the symbols. Okay, so that should be very easy to understand. In the book, actually, there are a lot of information about the endurance limit. So it's not that simple as my uh, slide. So I'm going to show you how the book is describing about the measurement of endurance limit. It's gonna be somewhere. And this is basically the slide came from the, the book the bookseller. And okay, so here's the part that's more details about endurance limit. So over here there is S represents stress. So SE is a endurance limit, but there's a version with the prime on the top. So the SE prime is like uh, some estimation without considering many effects. And there are a lot of pre-multipliers of K's. They are various kinds of factors to handle for different kinds of conditions. From here, you can see there are factors about surface conditions, size, load, temperature, reliability, and some other effects. Okay, so overall, if you multiply all the k's with the estimated endurance, that's the more accurate endurance limit at the end. So even you have this equation, is it correct? Who knows? Maybe this probably is this this has been developed tens of years ago. Maybe nowadays they are already researcher updating the equation. But at least you know it's a kind of research area based on a lot of experiments, collection of data, and experiments under various kinds of conditions. And there could be unusual conditions that is not considered right here. Let's say you put this in the space. All the knowledge we have learned on the Earth may not be valid for application in the space, where it is probably extremely cold or the pressure condition is different. So this is for usual usage, but and there must be some new research area working on this. Okay. I'm not from the material science, so I believe in the material division of our department, maybe some professor works on something like this. But anyway, This is good enough for us. And let's take a look at some of the factors. So for you to know about how people have done for estimating the endurance limit. Right here, this is K. Let's take a look at the SE prime first. So SE prime should be somewhere a bit later. SE prime. Okay, SE prime. Half of the some value right here. This is ultimate tensile strength. Ultimate tensile strength. Oh no, yield strength. Ultimate tensile strength. That's fine. So SE prime usually can be estimated by half of the ultimate tensile strength. So what does that mean? Without any consideration of the factors, after the cycles of 10 to the power of 6, what's the usual or estimated material strength? It's half of ultimate tensile strength. Around half. Okay? So that's very, very useful knowledge. Because if I apply certain force to introduce ultimate tensile strength, the stress level equals to ultimate tensile strength onto this table. I apply that super hard force. And since the stress is already reaching ultimate tensile strength, this is gonna be broken by that strong force. One shot, right? Now I will just reduce the force to half. So now I apply half of the stress in the level of basically half of ultimate tensile strength. Then how much cycle I can apply this half amount of stress onto this table, around 10 to the power of 6 times. So you kind of have a sense how much force this table can take and for how many times. Okay, that's very useful knowledge. Now let's take a look at some other case, all the case. First one is Ka. So Ka is about surface factor. And over here, whenever you see an equation that looks a little bit weird with some known information and some power value and some coefficient in the front, and for some reason you just have a feeling, hey, this is not from physics. You're right, this is from statistics. So usually people has done some research and realized, oh, Ka has some relationship with the ultimate tensile strength and following some kind of nonlinear behavior. There is some kind of nonlinear relationship between them. But that relationship is gonna change when the condition changes. So what researchers have done is they did experiments, tons of experiments. They realized, okay, they found when you do some cutting based on grounding or machining, different ways of the manufacturing process and surface treatment on your pot, and the factor and the power will follow certain values. Okay, and how come there are two A's? Because for different units. Okay, so If your ultimate tensile strength is in the unit of megapascal, use this column. If it's in kpsi, use this column. But the power, use the same one. Okay? So whenever you see something like this, certain people's name and okay, there's an article and there's some. This is like a. Let me explain to you what this is. This is based on someone's research. It could be you in the future. So these two person, maybe one is professor, the other one is a graduate student, and they published a research paper called Allowable Walking Stresses in the year of 1946, like 60, 70 years ago. So maybe whatever you are going to do, maybe 3 years later, may have an impact 50 years later. Yeah. So anyway, this book got those data from this article. So these guys have done tons of experiments to find out what are the conditions. So they published this paper in this Society for Experimental Stress Analysis. So this is what we call journal paper. Journals. Okay? So there are some jokes that we usually make between professors. What are journals? Journals are like technical magazines. And what are papers? Basically, just like a article, or it's like a journal is like a technical newspaper. And a journal paper, whatever paper you're writing, is like a technically written article that has been submitted for publication in some technical article magazine and being reviewed by a lot of professors. And if they say, okay, this is a good article, okay, approved, then the article is there and it has an impact in the research area. Yeah, so basically, these guys have done these. And over here, reproduced by blah, blah, blah. So these guys have done some research in 1946. And okay, so later on, this person published a book called Metals Engineering Design SME Handbook. And they put some of data into the book, or they reproduce what these guys, the first two guys, has done in the past, reproduce the experiments and put the new data inside the book, the handbook. And back in 1953, so it's like 7 years later, some of your data being officially reproduced and put inside a handbook so that someone who studied for a degree 50 years later can read your data. Something like that. So maybe this equation is just one person's thesis. He only contributed this in all his life. Yep. Okay. What's the second vector? Second one is a size factor. Again, coefficient and some power, and the main variable is the diameter. Okay, so why are we only caring about diameter? So when we have diameter, that means it's a cylindrical object. Because we don't bend this guy all the time. But for some cylindrical part inside a machine, like all the beam problems we have solved in the past few weeks, it will always carry some loads or its own weight. And there will be supports, no matter what kind of orientation you are placing it inside a machine. There's always gravity, and there's always certain reaction forces to hold it. So definitely that beam is being bended in a certain way or twisted or in a certain way. Now think about, let's say this is, okay, it's heavy. Okay, okay, there's a lighter one, someone's water bottle. Okay, so let's say this is a beam. Now I'm gonna apply a force from the top, okay, and then I'm gonna hold them from the side. So this is basically a problem we have solved earlier. Some force on the top, and then reaction force from the side. So it's gonna bend in this way, right? Being bended. So the top side is being compressed. The bottom side is gonna be stretched. But that's only for this configuration. Now, if I have a motor that is driving the shaft and turn it by 180 degrees, what's gonna happen? The top side goes to the bottom. So the top side was being compressed earlier. When it goes to the bottom, it's being stretched. So if you think about that particular point on the surface of the cylinder, this is time, okay? This is stress. Think about that particular point on the top. In my story, at the beginning, it's being compressed, so it has a negative stress. So after being rotated by 180 degrees, it goes up to being stretched. So as the motor keep on rotating, that particular point is being compressed and stretched consistently. So for all kinds of cylindrical part that rotates in all kinds of machine, it's always being bended reversely for tons of times. And think about how fast your motor is. We are counting about RPM, number of rounds per minute. Usually it's like 1,000, right? Thousands of rounds per minute. So in 1 minute, I already rotate this cylinder for 1,000 times. So every cycle, I bend it back and forth once. So how many times I bend this guy back and forth? A lot of times. In a minute, just a minute. So that's why when we are talking about endurance limit, we are talking about millions of cycles. Because usually that shaft will break when we apply millions of cycles of the force. And what's going to happen is the strength of the cylinder is going to drop. Okay, so are we truly allowing the shaft to reduce its strength to fatigue point after 10 to the power of 6 cycles? Actually, no. If we allow that, then your bicycle or motorcycle will, some of the shaft inside will bend after maybe several years. You won't allow that, right? But so as a manufacturer, you need to know how strong that shaft should be. So after 10 to the power of some value cycles, this won't fatigue. Fatigue won't happen. Okay, so the effect of, we need to consider the effect of fatigue for cylindrical components design. And this is about the geometry. They realize if you have a thinner or thicker cylinder, the factor may not be 1. Okay? Now, here, it's also telling you for axial load, there is no size effect. So this is purely for bending. So if you have a force that is applied along the central axis, basically like compressing it, the shaft is not causing any fatigue issue, only the bending, like what I have shown you earlier. Okay. Now, this is also size effect. Size effect. And there are some other that I talked about was for cylindrical parts, but there are some other considerations for different geometries. And why do we always see these kind of drawings in our textbook? Because we design a lot of cylindrical parts, we design a lot of rectangular cross sections, and we also design a lot of I beams and half of the I beams for construction, right? That's why when people design the I beam, because the geometry is quite complex and it's useful to have some measurement calculation done in the textbook so people can directly use it in the future when you design something that is having an IB, you don't need to do the integrals by yourself. Okay. Another factor is the load. So if you are having applied bending force on the shaft, so the coefficient is one. That means you got like 100% of the effect of fatigue. But if you have let's see, if this is smaller, that means your endurance limit is gonna be even lower. What is that? So if you twist, so earlier in the size effect, they don't care about the actual load. But for the load effect, actually, if it's an axial load or torsion load, the K is smaller. Smaller is actually bad because your endurance limit equals to tons of K's multiplying your estimated endurance limit, SE prime. So that's your final endurance limit. But if your endurance limit is lower, that means the fatigue effect is stronger. It makes your material weaker. So twisting is gonna make your material weaker. If you twist your shaft uh, certain cycles, it makes your strength drop even more. Okay, temperature. So under different amount of temperature, uh, there is a factor. Okay, they even use equations like this. So earlier we saw models like this, right? So this is more like a power law equation, right? And this is more like a polynomial. So different orders of polynomial. It could be something like this. A0, if you have second order. B1, A1, right? Something like this, right? Or you can have a higher order. So basically, researcher do some curve fitting to figure out how to compute those coefficients. And for power law, they compute the power and also the pre-multiplier. Okay? That's basically statistics. So actually in this course, in mechanical design, we need a lot of statistics. Many things cannot be derived by physics. How do you derive it? It's so difficult. So how do you know the relationship between this particular temperature and this K equals to this? So can you say, okay, this equation is exactly right? You cannot. It's just one estimation. So maybe in the future, one day you are doing some research and you start from some kind of physical theory and derive certain equation, and you found some equation that can replace this one, then maybe that equation can be put in the textbook. And remember, when I was a student, I went to a seminar in our school, and there was a presenter talking about pi. Talking about pi. So pi is a number with a lot of digits, infinite amount of digits behind the zero. So he is a researcher. I think he's a mathematician. He's trying to find what's the like a simple form that equals to pi. So whenever in the future you are going to calculate pi, you can just plug in the form and get the value. So I think he used some kind of supercomputer to find that equation, and I think he 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 I think he was using some kind of a computer mathematical trick or computer trick to figure out what's the closest simple form of pi. So I remember he claimed that equation he found can get absolutely correct digits for very, very long amount of them. I think 10 to the power of some value digits accurate. So he said uh, before him, there's no one can say that equation is wrong. But maybe in the future, some others can do even more accurate calculation to prove him wrong. So if some equation is having 10 to the something number of digit accurate after the zero, can you say it's not the exact equation? So that's always a debate between analytical approach and approximation. If you can approximate something so accurate, can you say that's the exact equation? So that was what that seminar was about. Anyway, just for you to think about it. Yeah, this is reliability. So with different amount of reliability, you may have different values. So over here, there's an important comment. The SE prime equals to 0.5 SUT is for only 50% of reliability. So what does that mean? That means after, let me open my file. That means after 10 to the power of 6 cycles, right here, and if I apply, if this is the SE I'm using, apply this force, and then fluctuate for 10 to the power of 6 cycles. And if let's say this is half of the endurance limit, okay, does that mean when I apply this amount of stress for 10 to the power 6 cycles, all the material breaks. No. But how many? So uh, under this condition, actually there are more information about this experiment. They found, okay, 50% of the material fell. So 50% reliability. So that means this curve represents 50% of reliability. But if you don't want your reliability to be so low when it's reaching the fatigue limit, then you need some more analysis. So definitely, if you are doing some experiments and you are looking for greater amount of reliability, definitely the curve will be on the left. On the left. Maybe I'm not sure if this is right at the tail, but definitely a little bit more to the left. What does that mean? If I apply the same amount of stress and I'm looking for greater reliability, maybe I can only last fewer rounds of cycles. And over here, I can have greater reliability. So less components will get fatigue failure. So over here, this means half of the components in your experiments have fatigue failure. And this means less fatigue. Less components has fatigue issue. So this course is not just about getting a right model, putting the right numbers, getting an answer. Okay, I got it right. I got the credit. This course is about the concept. As a mechanical designer, if you want to design for a component, what you need to know about. So before today's class, I never tell you about the fluctuating loads. Now after today's lecture, you now realize fluctuating loads is gonna weaken your material strength. Since it's gonna be weakened, you need to know how weak it's gonna be. So in your design equation, you will be applying certain values that considers the weakness of your material strength. So you are still conservative. Okay? So now let's talk about, I think it's a good time to talk about the equations. So there's a model called the yield line. So what's going on about this yield line? It's actually based on a very simple concept. So we have, this is time, and let's say this is our fluctuating load, and here is the mean value of the stress, and this is the amplitude of the stress. So what would be the extreme stress? The largest value is right here, right? This is an extreme. This is the maximum stress. So the easiest concept is that the maximum stress should be smaller than yielding, then you're fine. This is why you have an equation like this. That's the simplest model that we can have. The simplest concept. just protect the extreme case. Even though it doesn't happen all the time, it only the stress only reach this amount at a very short period of time and then release. Right? So if you count the time, maybe this only happened within 10% of the time. But we need to be safe. So even this is only less than 10% of time, we still design, like we still have a design equation to protect this particular uh, loading at that short time. Now, in this particular um, chapter, we will be making a drawing on the right hand side. So what is this drawing about? This is the horizontal axis is the mean stress, and the vertical one is the amplitude. And later on, we will be having design equation, different versions of design equations. They all have design variables of the mean stress and the uh, stress amplitude, basically sigma m and sigma a. And let's make a drawing of it. So if you make a drawing of this equation, you will see there is a red line right there. Okay, if you make a drawing of that. So if you stay on the left, right here, your mean value plus the amplitude is smaller than the yield strength. On the right, your mean plus your amplitude is greater. So this is basically fatigue value. Okay? And if it's on the line, then your material will have fatigue issue. So right on the line, this is where you will have fatigue. So we want to design to avoid a design point right on top. That's why we will apply a safety factor. And based on what we have learned in the past, how do we apply safety factor? We will have some value that is greater than 1 or equals to 1. Right at the bottom of the right hand side, apply a value right there. So our design equation will be offset. This is after safety factor. It will be like shifted inward because the left lower corner is a safe zone, right upper corner is a danger zone. And we don't want a design to be staying on the limit. We want a design to be stay away from it. So we shift the design equation toward the safe zone a little bit. By how much? By the value applied right there. So that would be the final equation right here. This is the final equation. And later on, since we have different versions of the models, we like to rewrite this equation into this form. This is the final form. We like to write it in this way because in the later model, it looks very similar. It's just having a different value somewhere. Okay? Should be very simple. But if one day, without today's lecture, if I give you this like a book content and you try to understand, okay, what is this drawing about? Sometimes it takes some time to understand what's going on. But after you realizing this is what this story is about, is nothing difficult. Okay. So I'm gonna move on to the next two models, which will be less conservative. So this model is the most conservative. Yield line. Most conservative. The next two models, they are less conservative. Okay, so this is a model called Goodman. And there are two things that's happened. First of all, for the mean value, if you, I should not erase this part. Time, mean, amplitude. So if you take a look at the mean value, for many of the times, half of the times, the stress level is actually lower than the mean value. And of course, half of the time is higher. So whenever we make a drawing of this, we kind of separate the effect of constant stress behavior or constant stress level and the fluctuating level. So this is the constant part. And this is the fluctuating part. Okay, we kind of separate them into two. So in the model of Goodman, and since there is always a constant for this fluctuating load, and many of the times is actually the stress level is lower. So for Goodman, it believes that if this mean stress level is not reaching ultimate tensile strength, it won't break. So if you only use the yield strength as the limit for mean value, it's too conservative. So the first idea Goodman applied is to be more conservative. Oh, no. It has to be more conservative. Yes, I'm talking about idea two. It has to be more aggressive on the mean. So you can actually have greater design space for the constant part because the stress level is not always up to the mean. Half of the time is actually lower. So that it allows the mean stress to be slightly greater. Greater to where? Greater to ultimate tensile strength. Okay, so that's the first concept Goodman applied. The second thing Goodman applied is he has another viewpoint about the fluctuating part. He thinks you need to be conservative about the endurance part because you are already aggressive on the mean part. Then if it's fluctuating a lot, it's on the fluctuating part. That fluctuation will make your material weaker more. So originally, in the yield line design, the fluctuating part has a limit, which is the yield strength. It only allows the fluctuating part to be as large as the endurance limit. So this is greatly dropped from yield strength to endurance limit. So the green line now being shifted to the blue line. By doing, what do you do to allow this? Basically, change the two values at the bottom of the equation. So underneath the mean value, you change it to the ultimate tensile strength. Under the fluctuating part, you change it to endurance limit. And if you want to apply safety factor, same right here. So this is after applying safety factor. So Goodman is both aggressive and conservative. So Goodman is aggressive here, but conservative here. So Goodman is aggressive about constant stress, but conservative about the fluctuating stress. That's why later on, there is a modified Goodman. So what is modified Goodman? Modified Goodman is a combination of, so take the yield line and Goodman. Basically, yield line plus original Goodman. So it's the modified Goodman is actually a set of two equations. Okay? What does that mean? This region is modified Goodman. The combination of both. So when you have modified Goodman, that means you are conservative for both constant stress and fluctuating stress. So kind of merge two concepts together. Okay?
Sorry.
Yeah.
Is a modified Goodman just kind of very similar to the Soderbergh model? Because
That's what I'm going to talk about later. So this is what you're looking for. The Soderbergh. The Soderbergh is basically one equation, but it wants to be conservative for both. And this is another model, Soderbergh. So Soderbergh right here is gonna take the conservativeness for both on the mean stress and the fluctuating stress at the same time in one equation. So right here for the Soderbergh model, you use the yield strength underneath the mean stress and the endurance limit underneath the fluctuating stress. So the Soderbergh model has the smallest design space. Design space is the most conservative one. Okay, and there are some other models that actually has been developed, which are more nonlinear. I'm not covering in this particular slide, but I can share with you. From those models, you will realize Soderbergh probably is too conservative. Okay, so I can show. Let me go to the textbook slide because there are some other nonlinear models. Okay, this. So this is like a overview of various kinds of models with different considerations of conservativeness And right here, the most original one is the yield line, which is conservative. And when you have a smaller design space, it becomes a little bit aggressive. So this one, what's confusing in different textbook is that some researchers said this line is modified Goodman, but some researchers said the combination of these two is Goodman. So it really is depends on how you want to describe it. So later on, when you use it, as long as you know what you're doing, I think it's fine. And over here, this one is the Soderbergh, the most conservative one. And there are two more nonlinear models. This is an ellipse, so in the shape of ellipse, and this is so-called the Gerber. Okay, so similar. They have a similarity. They are all curve-like, looking like a part of the ellipse, and that particular curve passing through the endurance limit and the yield strength. Or if you want to be a little bit aggressive, you shift the mean limit to ultimate tensile strength. That is the Gerber model. So it really depends on which model you want to use. There's not a right answer. Okay, so how do you use it? So later on, when you when you solve a problem. So let's say we have some problem right here. This is a shaft, and you have certain load. Okay, right, and you have reaction forces. So for this particular problem, the shear diagram looks like this, and this is shear, this is moment. Moment diagram looks like this, right? So you know, right here, you have the largest moment. Since it has the largest moment, so you have the largest stress because stress equals to 32 m over pi d cubed, right? So somewhere on top of on top of this circle has the largest stress. So if we take a look at that particular point, if my force is right like this, so this particular point right here is being stretched, so it should have the largest tensile stress everywhere inside the beam, inside the shaft, and that which is this amount. But this point rotates. So after it's being rotated to the top, it will have the largest compression stress. Right? So at the end, all the points on this parameter is gonna experience this kind of fluctuating load. And here is basically your stress max. So for all the points surrounding this shaft, what is the mean stress? The mean stress is actually zero because it goes positive sigma and then negative sigma. So the mean is zero. And the amplitude is the stress, maximum stress, so 32 m over pi d cubed. Okay? So for this simple problem, am I fluctuating anything? Actually, no. I'm just spinning the shaft. But the stress inside the shaft is fluctuating by itself. And if I apply these values in our design equation, the mean stress is gonna be 0, and the fluctuating stress is gonna be somewhere maybe here. Okay. So at this right here is like a 0 and the sigma max. Okay. So as long as my sigma x, the sigma max is not too high, I won't have fatigue issue. But if it's up to certain level right here, then after a certain amount of cycle, my shaft will bend due to fatigue. If I have even greater bending stress, that means the fatigue effect happens quicker. So if my design is right on top of here, if my sigma max is right there, that means after 10 to the power of 6 cycles, I will reaching the limit of fatigue with 50% of rehabилity. So that means if I have 10,000 shafts being designed this way, and they all carry this amount of load and rotate in a certain way, and after all the shafts rotate 10 to the power of 6 cycles, 50% of the shafts will have fatigue issue. So that is what this analysis is about. And as mechanical engineers, we will never want our shaft to have such a high failure rate, right? Okay. Some other example. If I have, in this particular example, the mean value is 0, but if I have stress that fluctuates, so another case is like the load fluctuates. So this is my T, this is my force, and my force fluctuates. So there will be a mean force and a force amplitude. In that case, I may need to study the shear diagram and the moment diagram separately. So since the force fluctuates, so my shear diagram, of course, fluctuates as well. Right? And because of the fluctuating load, my moment fluctuates. So this guy by itself fluctuates. So right here fluctuates. So the problem becomes more complex. But this is like this when you have rotation. So in this particular case, if my load is also fluctuating. Earlier, it's a constant load but rotation. So I already have this result. Now it's fluctuating loads also rotating. So my stress fluctuates in such a way, it's like a fluctuation on a sine curve. So in this case, based on what we have learned, I should consider right here as my sigma amplitude. Because that's the extreme case. So in this particular case, what's going to happen is mean is the same, but the amplitude basically increases. Depends on how fluctuate your applied force is. So that's only pushing this point up even more. How about if we have this fluctuating load, but the shaft or the beam structure doesn't rotate? It's not rotating. It's only a supporting beam, but it's carrying this fluctuating load. In that particular case, since it's not rotating, we don't have this sine wave behavior because the point that carries the bending bending moment, the tensile stress, it's always having a tensile stress. It doesn't rotate to the top. So in that case, if I have fluctuating load plus stationary shaft, in that case, my stress diagram will look like this because of the fluctuating load. So I will have a positive stress mean value, and I will have a positive stress amplitude. Okay, and let me remind you about what I have shown you earlier. If I have fluctuating load but rotating shaft, then the diagram looks like this. It's like a sine wave, but because of the fluctuation, I even have greater amount due to the fluctuation. Okay? And even earlier, I had a constant load, but rotating shift. In that case, only the sine wave. Okay? So you need to know about your problem and study the stress variation along time and figure out what's the proper value of the mean value and what's the proper value for the stress amplitude. And then plug into the drawing. Then you know where your design is. So in this particular case, if you have fluctuating load but stationary, so you have both positive value for the mean and both positive value for the amplitude, then your design point may be somewhere here. Let's say somewhere here. Okay? So based on specific model, you are already at the limit. But for different models, you may have a greater, you still have some design margin. Okay? So I want to talk about last one thing. So later on, when we apply an equation, let's say Soderberg. So Soderberg said mean over yield strength, amplitude over induced limit. Okay? So when I solve a problem, I plug in this value. So this is from my stress analysis. And these two are about material property. And this is basically safety level you are looking for. Okay? And of course, your stress analysis based on what you're doing, basically it's related to external loads. It's related to geometry. Is it related to material strength? No. Because stress equals to 32 m over pi d cubed, right? Or if you have shear stress, 16t over pi d cubed. So this is about geometry, this is about loads. And of course, if you have different cross section, you will have different I or different J, the area moment of inertia for bending and twisting, but that's related to geometry. Okay? So only thing related to the material property is right here. And the stresses are related to how much force you apply to the material, to the part, and the geometry of the part. And this is safety level. So once you have done some calculation, let's say you end up with n is smaller than 1 over, let's say, certain value like this. If you are computing for this. So what does that mean? It's like it actually, you can view this as a drawing. You are having some design equation, design limit, okay? And you are having some certain safety margin. Okay, and N represent how much safety margin you have. So whatever design point you have, when you meet N equals to this level, that means your design point is somewhere on the dashed line with certain value of N. That means you still have certain level of safety margin. So the margin is there when N is larger than 1. When you are on the limit, that means N equals to 0. If you are away, that means N is smaller than 1. That is not safe. Okay, so try to understand what safety factor means in a fatigue problem. It actually means how much safe margin you have. And it's in a level of values that is close to 1 and usually larger than 1. The greater it is, the far away your design is further away from fatigue. Okay, so I think that's everything I want to talk about today. In tomorrow's lecture, I will introduce the next slide and solve some problems. Let's also check the lecture progress. We are 21st. Okay, yeah. So tomorrow we will continue on the fluctuating loads. Okay? I am still having some events later on. Okay. Are you guys okay with the course? I know that I didn't teach too much, but I spent quite some time on the concept. I hope you can learn from the concept. I'm not trying to force you to memorize equations because eventually you forget about it. But the concept you can memorize. Okay, thank you. Make sure you do the attendance check if you didn't do it. Okay, all right.